Hi everybody, this is Austin Haga here to give you another lecture from OpenStack's Intermediate Algebra. Today we're going to be talking about rational expressions and functions. The learning objectives here start with an introduction to what a rational expression looks like. We'll look at some variations of that and determining for which values they are undefined. Then we'll talk about how to simplify rational expressions before we discuss the operations of multiplication and division. So here you can see a few different examples of what rational expressions might present as. For instance, here you see that's just in the form of some monomial divided by another monomial. They can get more complicated. I may have, as you see in the other two examples here, some binomial that matches to one of the special product forms. So for instance, the denominator for this first term, x squared minus 9, is a difference of squares. So there's some connection here between rational expressions, the operations that we use for them, and fractions. You'll see at the top, rational expressions are defined as polynomials in the form of a fraction. So p over q here actually represent polynomials. So rational expressions can come in lots of different forms and flavors, but at the end of the day, we focus on reducing them and performing operations much in the same way that we do fractions. And so I'll refer back to those notions along the way. What's interesting about rational expressions is that they're actually not defined for some specific cases. Especially in the context of an equation, this becomes important because your rational expression could be something that causes the equation to be unsolvable, or potentially an equation could have a solution that does not actually give me a true statement when I plug it back in because of the rational expression. So why and how does this happen? Well, here's a few examples where we're asked to determine the values for which the rational expression is undefined. So let's start there. Basically, there's only one way in which we can cause a rational expression to be undefined, is if we cause division by zero. So take a look at, for instance, part A here. Basically, I want to know what value causes this expression to be undefined. Well, if we take the denominator 3c and say, well, if it was to be equal to 0, it would be undefined. So that is our sort of stipulation here, is that it cannot be equal to 0. So a lot of times what we'll do is say, just to set the denominator equal to 0 and solve for your variable. So in this case, it's fairly trivial. If I try to divide by 3 on each side, I get that c equals to 0, meaning if I replace c with that value, I would cause division by 0 in the entire expression. So this allows me to identify what the rational expression is undefined for, and it will also give me the restrictions if I'm using this in the context of an equation. Let's look at another example on this page. For instance, part C here gives me the expression x plus 4 divided by the trinomial x squared plus 5x plus 6. For part C, this expression is only undefined if the expression in the denominator is equal to 0. In other words, we don't want this to happen. So what value causes this to be equal to 0? In this case, we can use a technique called the AC method to factor by looking at the coefficients here at the beginning and end of the expression and asking what two values multiply to give me 6 but add together to give me 5. So by factoring, I would discover that x plus 3 and x plus 2 are the binomials that would multiply together to give me back the original expression. Using the zero product rule and setting each of those factors equal to 0, I would discover that if x were to be equal to negative 3 or negative 2, I would cause division by 0 in the denominator. So those are my restrictions. As long as x isn't equal to those two numbers, the expression will be defined. So factoring, as you just saw, plays a pretty critical role for rational expressions. Simplifying rational expressions is done in the same way that we would simplify fractions, which is why I present here the equivalent fractions property. Recall that The equivalent fractions property states something similar to what you see here. If I can factor my numerator into multiple terms, and they seem to have common terms in both the numerator and denominator, they'll cancel each other out. What's critical to understand, though, here is that the numerator and denominators have to be factored, meaning as a product. I can't, for instance, look at the first expression here and say, oh, well, just because there's an x here and here, they'll cancel out. These binomials actually don't match, and so it would not be the case that these are common factors. We can say in the second example, though, that, for instance, x divided by x here would cancel out, reducing this expression to just 2 over 3. So as long as it's as a product, then we can sort of reduce the equivalent expression here, but not so much if it's in the form of a binomial term. So these would have to match exactly for me to reduce the expression. But let's take a look at some more examples. Here is more typical of the type of problem you'll be presented with. I'm asked to simplify the expression here, x squared plus 5x plus 6 divided by x squared plus 8x plus 12. So my task is going to start by trying to factor, using all the techniques that we've discussed in previous sections. In this case, it looks like since these are two trinomials and the coefficient on the square term is 1, I'm going to use the easy version of the AC method. So we just looked at the example a moment ago where we had x squared plus 5x plus 6 and discovered that it would factor to give me x plus 3 and x plus 2. My denominator would have a similar scenario where I would look at, what are the factors of 12 that add up to 8? And in that case, I would find that x plus 6 and x plus 2 satisfy those criteria. So all we've done is rewrite the expression in its factored form here so that we can then identify, okay, what is it that they have in common between the numerator and the denominator? So the binomial here, x plus 2, we would say crosses out, leaving me with the reduced version and the answer here, which is x plus 3 over x plus 6. So factoring plays a critical role here. We've got to be able to identify the appropriate technique quickly in order to answer these types of questions. And this is before we even get into how do I perform operations with these types of rational expressions. So simplification is a critical skill set. Let's look at some more examples. Here's a slightly more complicated one. And again, it's not quite obvious how, but I do know that I need to factor and try to identify something that might be in common between the numerator and denominator. So typically, what we would start with is identifying the greatest common factor for my expression in the numerator as well as for the expression in the denominator. In our case, we could actually identify 3 as a GCF amongst all the terms in the numerator. So if I remove a 3, my expression looks like a squared minus 4ab plus 4b squared. And in the denominator, my two expressions have a 6 in common. So that can be removed, and the leftover expression would read a squared minus 4b squared. So step 1 typically is to consider, do we have a greatest common factor that we can remove? And then secondly is to identify the factors of what's left over. And it could be that we need to use the AC method, or we might need to do one of our special products. So in this case, if you look at the numerator, I have something that looks to be in one of these special product forms. It's maybe not obvious, but for our example here, we have something in the form a squared minus 2ab plus b squared, which should factor to give me a minus b squared. So again, it's maybe not obvious that it matches to this format, but if you look at our expression, it can be sort of rewritten in the following way. We could have it as a squared minus 2 times a times 2b plus 2b squared, like this. And if you study carefully the sort of expression here and what we have written, you'll notice that my particular example is in fact one of these special products. Similarly with the denominator, we also have a difference of squares. And it may not, again, be quite so obvious at the outset. But a difference of squares, like a squared minus b squared, is always going to factor to give me a product of conjugates. So if that's not obvious, again, we can try and rewrite the expression here. A squared obviously is a square term, but 4b squared could be written as 2b raised to the second, like this. So if we are able to factor everything down to the sort of nitty-gritty here, we should be able to then identify if they have anything in common. So rewriting this expression one more time, our numerator could be re-expressed as a difference of squares. That would be a minus 2b squared. And the denominator, of course, a product of conjugates. So that would be, again, 6 times a plus 2b and a minus 2b. So now we can start identifying what is the common factor, and it appears that at least one a minus 2b shows up in the denominator as well as in the numerator. Since this has an exponent of 2, we assume that there's actually 2 of these a minus 2b's, and so what would be left over is at least 1 in the numerator. My coefficients 3 and 6 will be reduced to 1/2, so I still have at least a 2 down here, along with the other factor a plus 2b. So there is my solution, whittled down to its simplest form. And this is, again, sort of an initial step. Typically, we'll be asked to simplify after we perform some type of computation. So not only will we be able to multiply and divide or add and subtract things together, but as would be the case with fractions, we might have to then simplify that result. So let's look at another example here that looks at something called opposites in rational expressions. This is a case where we have something that's pretty close to the same in both the numerator and denominator, but the order seems to be off. So a specific example might be something like x minus 2 versus 2 plus x, or negative 2 plus x. Not quite the same, but pretty close. And so what this property tells me is that if the sort of expression is opposites, they will reduce to -1, as opposed to canceling each other out. And the specifics of this are highlighted down here, but I think it's best to look at a specific example in the context of a question. So let's take a look. So here's an example, again, where we're just asked to simplify. It looks like there's not really any GCFs between my expressions in the numerator and denominator, so I'll start by trying to factor everything. In the numerator, we have a trinomial, so we can use the AC method and ask the question, what are the factors of -32 that add to give me -4? So in our case here, we might say, well, 8 times 2 would get me to 32, but which term gets the negative sign? We want them to add to be negative, and so in this case, we'd say, well, x plus 4 and x minus 8 should satisfy those criteria. My denominator is actually another difference of squares. 64 is the same as 8 to the second power, and so it gives me a product of conjugates. We would have 8 plus x times 8 minus x. So it seems like we have pretty close to the same expressions in the numerator denominator, specifically dealing with the x and 8 values that you see here, but they're not quite exactly the same. And so we would be able to recognize that maybe these are close but not quite going to divide to give me 1. They're going to actually divide to give me -1. So how do we express the solution here? Well, we just flip the sign of everything. We can make our fraction negative and leave it in the form that you see here. So it does not reduce any further from here. I just want to present at least one example of instances where we have these sort of opposite factors that don't exactly go away, but they do reduce to -1. So look out for these. They're kind of rare, but they can trip you up on occasion. Well, now let's start looking at examples where we're asked to perform some computation in addition to simplifying the answer. So when we talk about multiplying rational expressions, again, it's done in much the same way that you would expect multiplying fractions goes. If I have some kind of fraction like 1/3 times 2/9, we would multiply the numerators, multiply the denominators, and there we get our solution. What's typical of that computation, though, is that you then may have to turn around and simplify the solution further. Now, I don't in this case, but typically when we perform the computation, we then have to consider, okay, can I factor and reduce the expression even further? So let's look at a specific example or two. Now this is a nice, much more complicated looking expression. I'm asked to factor all the numerators and denominators, multiply them together, and then reduce the outcome. So it's best to start with just trying to simplify the numerator denominator by factoring. So let's take a look at the first fraction. I've got 2x over the trinomial x squared minus 7x plus 12. My numerator is not really going to factor much. It's just 2 times x. But I have a trinomial that we can factor using the AC method. So factors of 12 that add up to -7 would be -4 and -3. In my second expression, my numerator is a difference of squares. X squared minus 9 can be rewritten as x squared minus 3 squared. And so it would factor to give me a product of conjugates. Lastly, we have 6x squared, which I can sort of rewrite as an expanded form. So 6 times x times x. And even this we could rewrite slightly in the hopes that we identify factors of 6 that would be in common with our numerator. So if I wanted, I could go all the way down to the prime values and even expand the exponent to make for a little bit easier task. So I've factored everything. Now let's actually do the multiplication. So again, to find the product, we just multiply the numerators together and multiply the denominators. But I'm not really interested in multiplying everything together. I just want to put them into the format that we know would be the solution. So 2x, x plus 3, and x minus 3 all get multiplied together in the numerator. In my denominator, if I rearrange just a little bit, we would have the product of 2 times 3 times x, and then of course my binomials x minus 4 and x minus 3. So technically that's my solution. It's by no means simplified though. So we can identify common factors much more easy now. If we cross out those that they do have in common, we'll find what's left over as our solution. So looking at what remains here, my answer has to be x plus 3 in the numerator divided by 3x times x minus 4. So you'll notice that your answers here may take on some crazy looking formats, but really that's all that's left. We get the solution here in its simplest form, and once we perform the computation, again, we don't really multiply things back together, and it's a lot easier to simplify, leaving things in their factored form. Let's look at another example. Here is a much more complicated version where I'm asked to multiply these two rational expressions together. And what makes a task like this difficult is how well you identify the proper factoring technique to perform. So let's look at the numerator here. 3a squared minus 8a minus 3. This is a trinomial in the hard form where the square term has a coefficient greater than 1. So in order to factor here, I would need to be able to identify what two numbers multiply together to give me a times c, that also add together to give me the middle coefficient, -8. And since this is the hard version, once we get a solution, we actually have to factor by grouping. So what are the values for m and n here that satisfy our criteria? Well, if we use m equals -9 and n equals +1, they'll multiply together and add together to be the values that we need. So what does that mean? Well, it means that our expression can be split into two parts. The middle term, at least, will be split in this way. And to factor by grouping, we will identify the GCF amongst the first two terms and remove it, leaving us with a binomial, and repeat the same process for the second pair. So 3a squared minus 9a. They seem to have a GCF of 3a. And if I remove that from each term, I'm left with a minus 3. My second pair of terms really don't have anything in common other than 1, and frankly, it looks like an a minus 3 binomial already. So if we remove just a 1 here, we should still come up with that same binomial. So if a minus 3 is the common binomial, that means this numerator will factor to give me a minus 3 and 3a plus 1. So when I find the product here, I'm going to just stick my factored version of each of these numerators into the numerator of this larger expression. So looking at my second numerator, if it's not obvious, this is a trinomial again that follows one of our special products. In that case, we have something like a squared plus 2ab plus b squared, which factors always to give me a plus b squared. So finding the a and b values in this case would mean looking at how to rewrite the expression, right? So obviously the first term is a squared. Instead of 10a, we could also write this as 2 times a times 5. And then lastly, b squared. Instead of 25, we could write it as 5 squared. So it does actually match to our format here, which means our particular expression is going to multiply together, or rather factor, to be a plus 5 squared. My denominator for the first term is the difference of squares, so a squared minus 25 is going to factor to give me a product of conjugates. So there's one other piece to the puzzle. So by now, hopefully you can kind of tell that the challenge here is really just determining the appropriate factoring techniques, right? So the last one we got to do is the denominator of our second expression. Then we can start trying to cancel out all the other common factors that we see. Again, that last denominator, 3a squared minus 14a minus 5, I would need to identify, using the AC method, the appropriate values that satisfy the conditions, what values multiply together to give me -15, and also add together to give me -14. So sort of similar to before, we can use -15 and +1 for our terms. If we re-express the middle term, -14a, as -15a plus 1a, we can start using our factoring by grouping technique to finish this off. We can identify 3a as the GCF for the first pair of terms, leaving me with the binomial a minus 5. And just like before, we end up with another a minus 5. And so our factor for that last denominator is going to be a minus 5 times 3a plus 1. So just to be clear, these are the sort of 4 techniques needed in this case to identify all the factors of the given expression. I've got them multiplied together, but it's still not reduced. So we use special products for at least 2 of these and the AC method for the other 2. But you can imagine this could get as complicated as you want. Our case is not quite done now, but we need to see what are the factors that we have in common. So I see, for instance, that at least one a plus 5 would cancel out with an a plus 5 here. We also have a 3a plus 1 canceling with the 3a plus 1 here. And so finally we get a solution, which maybe I can squeeze in my final answer here then is going to be a minus 3. I do still have another one of the a plus 5 values, the binomial here. So a minus 3, a plus 5 divided by a minus 5 squared. Since there's 2 of these, we can rewrite it as an exponent. So there finally I get my solution. So the actual operation here typically is not the challenge. It's identifying all the correct factored versions of these expressions. So if you find it difficult to start a problem like this, I would suggest having handy a short list of factoring techniques. Let's look at the other operation of division now. So we talked about rational expressions and fractions being very similar. When we talk about dividing rational expressions, the key idea again is to remember how we did with fractions. We keep, change, and flip the expressions. This is still true, and it will essentially become a multiplication problem, similar to what we just practiced. So let's look at just a couple examples here. I'm asked in this case to simplify the following expression. I've got a binomial in the numerator, x cubed minus 8. In the denominator, a trinomial, and I'm dividing by another binomial expression divided by 6. So how do I start this problem? Well, again, we need to set the problem up appropriately. We can keep the first term as is. We will need to factor this at some point, but we can keep the first term as is, change from division to multiplication, and then flip our second expression. So how is it that I can rewrite my numerator and denominators in their factored form? So in the case of my numerator, x cubed minus 8, this is a special product. This is a special product where we have a cubed term, or a difference of cubed terms. So x cubed minus 2 cubed is how that could be rewritten, and it turns out the factored version is going to be a minus b, a binomial, and then we have a squared plus ab plus b squared. So anytime you have a difference of cubes, we can factor using this special product rule, which means my numerator here would end up giving me x minus 2, and then times x squared plus 2x plus 4. And obviously 6 does not really factor. So if we want, we can maybe write it as 2 times 3 or just leave it as 6. Seems like I should have left it since I can't write without having this pen spike on me. There we go. For my denominators, I have in the first term here 3x squared minus 6x plus 12. That has a GCF that we can remove of 3. And then we would be left with x squared minus 2x plus 4, which is another expression that could be written using our special product rule. This is in the form of an a squared minus 2ab plus b squared. We could also use the AC method and ask what are the factors of 4 that add up to negative 2. So it actually doesn't appear that it matches to this form exactly, but it's pretty close. If we think about factors of 4 that add up to negative 2, we can't really come up with any. 4 times 1 could multiply to give me 4, but they don't add to negative 2. Obviously, 2 times 2 gets me to 4, which would be the only other pair of factors. And so it seems pretty close, but actually it doesn't match this form enough, nor can we use the AC method to factor it fully. So as odd as that seems, all we can do is remove the GCF and rewrite the expression. My other denominator is x squared minus 4. This one does actually match to a difference of squares, which again would factor to give me a product of conjugates. So x squared minus 2 squared is going to factor to give me x plus 2 and x minus 2. Now we have all of our factors, and my goodness, there's quite a lot of them, and they look kind of odd. Instances like this where perhaps something seems to factor but doesn't is maybe uncommon, but it can happen. So moving forward, I can see that, for instance, x minus 2 and x minus 2 are going to reduce. My 3's here will reduce. And I think that's really all I'm left with. Rewriting to get my solution, I've got 2 x squared plus 2x plus 4 in the numerator, and the binomial x plus 2 along with the trinomial x squared minus 2x plus 4. So for something that's simplified, it still is quite complicated. Although this is division with rational expressions, so who knows what the expression will look like by the end of it. Again, I need to know lots of different factoring techniques to get through a problem like this. The task is similar to multiplication, however. We set the problem up using our keep, change, flip idea, and then work through all the factoring techniques necessary to arrive at our expression as you see on that second line. Once we cancel out what's in common, we're all done. So let's take a look at just one other instance here, talking about multiplication and division of rational functions. Function notation is often really confusing for students, so I want to take a moment here to show you an example of a question that may be asked using that notation. Typically, when we talk about rational expressions and we want to perform some computation, it'll be given to me in the form that you see here. They say divide or multiply the rational functions together, right? So these are polynomials that we can either put into a fraction form, or instead of doing some operation, we could be asked to find what's called the domain of the rational function. Now, the way that we talk about whether or not a rational expression is defined for certain numbers is very similar to asking what's the domain of that expression. So you can see here that to determine that domain, we set the denominator equal to 0 and solve. Those are all the values that expression can take on and still be defined. In other words, all the values that don't cause the denominator to be equal to 0. So here's an example. I'm asked to find the domain. Given my expressions here, it's helpful to think about whether or not any of the numerator and denominator factors would cancel each other out. For instance, in the numerator, they have a common factor of 2x that could be removed, leaving me with x minus 7 as one of the factors. Similarly, in the denominator, they have at least a GCF of 4 that could be removed. And while it doesn't quite simplify everything all the way, I'm left with what you see here for my trinomial. So can this be factored further, and does that help me answer the question of what is my domain? I don't want to start by just immediately setting this equal to 0, because the numerator could influence which pieces, or rather which values, cause that expression to be undefined. So factors of negative 12 that add up to negative 4, well, in this case, we might say that negative 6 and positive 2 would work. So partly I can factor further to get my expression in this form. X minus 6, x plus 2. Nothing really seems to cancel out between the numerator and denominator, and so it was not the case that my numerator expression influenced what the domain of the expression is. However, we're not always guaranteed that to be the case, and so we can, in this instance, take our already factored expression, for the denominator at least, and say, well, this expression should not be equal to 0. So how do I solve? Well, this is easy to apply. We use the zero product rule and say, well, if we let each of those factors be equal to 0, in other words, x minus 6 can't be equal to 0, x plus 2 can't be equal to 0. What do I do with the 4 here? Well, if we try to divide the 4 out of each side of the equation, it kind of just disappears. And so partly any numeric value like this is just going to go away, and all we're left with are the factors. So x minus 6 can't be equal to 0, and x plus 2 can't be equal to 0, which means my domain is anywhere x is not equal to positive or negative values. So here is my domain. How do we state this? Well, we might write it in what's called the set builder notation, where we say that the domain is given in my curly Q brackets for values of x where x is not equal to 6 or negative 2. So on occasion you might see it in this form. So finding the domain again revolves around setting the denominator equal to 0 and solving. In most cases this will be sufficient. Be aware though that sometimes factoring your expression or simplifying your expression first is required to get at the domain. That's all for this section. We'll see you on the next one.